Good morning. In the last lecture, we defined the dual code of a linear code C. The dual code of C is the set of all vectors that are orthogonal to every vector in C. We saw that if C is an NK linear code, then its dual code is also a linear code of length n and dimension n minus k. We defined a generator matrix for the dual code to be a parity check matrix for the code C itself. We saw that a generator matrix for C in standard form immediately gives us a PCM for C. In today's lecture, we'll see that the PCM for a code C tells us a lot about the distance of the code itself. I'll summarize what we've learned about linear codes. In particular, the nice relationship between a linear code and its dual code. So here, C is a linear code of length n and dimension k over a field F. G denotes a generator matrix for C. So remember, this is a k by n matrix, whose rows form a basis for C. Hence, C can be described as the row space of G. C perp, the dual code of C, is also a linear code of length n, and it has dimension n minus k over F. We have this nice relationship that the dual of a dual code is the code itself. H denotes a generator matrix for C perp. So a matrix whose rows form a basis for C perp. H is an n minus k by n matrix. C perp can be described as the row space of H. Now, by definition, a generator matrix for C perp is a parity check matrix for the code C. And we can describe C as a null space of H. Hence, code words can be characterized as vectors x that satisfy H times X transpose equals 0. Analogously, a generator matrix for C is a parity check matrix for C perp. C perp can be described as a null space of G. And so code words in C perp can be characterized by the vectors x that satisfy G times X transpose equals 0. Here's the main theorem for this lecture. It's a way of saying something about the distance of a linear code by examining any PCM for the code. Let H be a PCM for an NK linear code C over a field F. Then C has distance at least S, if and only if every S-1 columns of H are linearly independent over F. So the theorem gives us a lower bound on the distance of a code by examining the columns of any PCM for that code. Let's prove the theorem. I'll denote the columns of H by H1, H2 up to Hn. I'll first prove the converse implication, and I'll prove its contrapositive statement. So suppose that the distance of C is not at least S. So I'm assuming that C has distance at most S minus 1. Let C be a non-zero code word of weight at most S minus 1. This code word exists because C has distance at most S minus 1. Now, without loss of generality, let me suppose that the non-zero components in the code word C appear in the first S-1 components of C. In other words, the components of C from the sth component to the nth component are all 0. Now, since C is a code word, H times C transpose is 0. And hence, C1H1 plus C2H2 plus CNHN is 0. Now I've noted that the coefficients cs up through cn are all 0. And so this linear combination becomes c1h1 plus cs minus 1 hs minus 1 equals 0. Since at least one of these coefficients is non-zero, this is a non-trivial linear combination of the first s minus 1 columns of H that gives a 0 vector. And so the first s minus 1 columns of H are linearly dependent over F. Let's prove the converse. So suppose there is a set of s minus 1 columns of H that are linearly dependent over F. Without loss of generality, I'll let these be the first s minus 1 columns of H. So there exist scalars lambda I, not all 0, such that this non-trivial linear combination of the first s minus 1 columns of H gives a 0 vector. Now let C be the vector obtained by taking these s minus 1 scalars and filling out the vectors with 0 to get a vector of length n. We'll note that C is a code word since H times C transpose is this expression, which is 0. But the weight of C is at least 1 and at most s minus 1. And hence the weight of the code is at most s minus 1. This means that the code C has distance at least 1 and at most s minus 1. And this proves the main theorem of this lecture. As an immediate corollary, I can say that if H is a PCM for a linear code C over F, then the distance of C is the smallest number of columns of H that are linearly dependent over F. Let's do some examples of this corollary. Here's the first example. In slide 64, we saw an example of a 5-2 linear code over Z3, and we wrote down this PCM for the code. H is a 3x5 matrix over Z3. Note that no single column of H is linearly dependent over Z3. A single linearly dependent column would have to be the 0 column, and we see that H doesn't have any 0 columns. And so by the theorem, the distance of C is at least 2. We can also see that no two columns of H are linearly dependent over Z3. In other words, scalar multiples of each other. So, for example, the first column of H is 2, 1, 0. And its scalar multiples are 0 times that column, 1 times the column, and 2 times the column, none of which is a second column of H. So again, by the theorem, we conclude that C has distance at least 3. Now there exist 3 columns of H that are linearly dependent over Z3, namely the first, third, and fourth columns. The first column of H minus twice the third column minus the fourth column is a 0 vector. And so by the theorem, the distance of C is not at least 4. Hence we conclude that C has distance exactly 3. We saw this in the example in slide 64, where we listed all the 9 code words and found that the smallest weight of a non-zero code word is 3. Let's now consider binary linear codes. So let H be a PCM for a binary linear code C. In this case, the scalars are the elements of the binary field, so 0 and 1. A scalar multiple of a vector is either the 0 vector or the vector itself. There are no other scalar multiples of that vector. So we see from the theorem that C has distance 1 if and only if H has a single linearly dependent column, in other words, a 0 column. the code C has distance 2. If and only if its distance is not 1, and it has 2 linearly dependent columns. So in other words, H has no zero column, and 2 columns of H are identical. Similarly, C has distance 3, if and only if the columns of H are non-zero and distinct, which means the code doesn't have distance 1 or 2. And there is some column of H that's the sum of 2 other columns. That would give us 3 linearly dependent columns of H, and hence by the corollary, the code C would have distance exactly 3. One can continue making similar statements about the distance of C, but these aren't useful for determining the distance of a code when doing hand calculations. Instead, we'll use the theorem and its corollary later on in the course as a theoretical tool for determining the distance of infinite families of linear codes. Here's my third example. Let's find a 743 binary code C. So I'm using 3 parameters to specify the code: its length, its dimension, and its distance. I'll construct the code C by first constructing a parity check matrix for C, and then deriving a generator matrix for C. So a PCM for C should be an n minus k by n matrix, so a 3 by 7 matrix. That has rank 3. And since C has distance 3, the columns of H must be non-zero, distinct, and some column of H must be the sum of 2 other columns. This will guarantee that H is a PCM for a binary code of length 7, dimension 4, and distance 3. So let's construct the PCM. So H is a 3 by 7 matrix, and its columns have length 3. I can't use a zero column, and I can't repeat a column. So I must use each of the 7 non-zero binary columns exactly once. I've done this here so that H is in standard form. You can check that the columns of H are non-zero, distinct, and column 4 equals column 1 plus column 2. Also note that H has rank 3. So H is indeed a PCM for a binary code of length 7, dimension 4, and distance 3. Since H is in standard form, we can write down a GM for C. Namely, if we consider H to be of the form the identity matrix and the matrix A, then a GM for C is minus A transpose and the appropriate identity matrix. Note that G is a 4 by 7 matrix. To summarize, C is a code of length 7, dimension 4, distance 3, so it's a single error correcting code. It's a binary code, and C has 16 code words. A nice feature of this example is that we were able to determine the distance of the code without explicitly listing all the 16 code words. I'll conclude this lecture by noting that the code C is a Hamming code of order 3 over Z2.
We'll see next the first infinite family of linear codes, called Hamming codes. These are single error correcting codes, and we'll see a simple decoding algorithm for these codes. Have a great day!